Hello, this video covers the homework from Unit 7, Module 1b. In case you are not able to come to office hours, these are the questions most often asked. Here we have a product, and we're asked which one of the reactants, 1, 2, or 3, with HCl will produce the product. All right, so one thing we have to keep in mind are the three acids will react here with the alkene, the double bond, in 2 steps. We also have the sulfuric aqueous, nitric aqueous, or just H3O, H2O, and this will react in 2 steps with the double bond. Okay, so what we're looking at is that if we have a chlorine present at the site given, there's probably an H that we could put to the left of it, or we can imagine there was an H to the right of it. And in that case, we could put a dash here, like the double bond might be present there, or it might be present here. And when we look at the reactants, there are 2 substances that have double bonds there that would have this product given as a major product. Right, so let's take a look at the mechanism. So what we expect here in the 2-step mechanism is that the nucleophile initiates the reaction and points at the electrophilic center, breaking the bond and giving the electrons to chlorine, producing a carbocation at 2 different spots. So we make a CH bond, right, and a carbocation. Well, to analyze the problem on what is major and minor, we count the number of carbons that the carbocation is attached to. So we see in the top one, it's 3rd degree carbocation because there's 3 carbon atoms. In the bottom one, it's a 2nd degree carbocation because there's only 2. So in this case, you want to make sure that you see that chlorine will always react at the site of the carbocation in step 2. Right, so for this is going to be our major and minor pathways. Okay, so Roman numerals 1 and 2 would both have major products there because in both cases chlorine has a tertiary carbon. Right, here we're going to investigate exactly what the first step is. So we know it's 2 steps, but let's look at the first step in detail. The double bond reacts just like we saw in the last problem, breaking the acid bond. Get 2 carbocations that are possible. Could have a carbocation on the interior carbon or on the exterior carbon. So since by induction, the 2nd degree carbon is more stable, the 1st degree carbon is less stable, and when we look at so this is definitely not going to happen because they're not going to be the same energy, and this is saying, is the primary more stable than the secondary, or is the secondary more stable? And that would be correct. Okay, now we have some data. As we mentioned, is the secondary carbon. So we need to have data to be able to assign the correct mechanism. Right, so what we want to do is, first we're going to find out what is the relationship with the nucleophile in the rate law. Okay, so to do that, we're going to have to analyze the data. So let's take a look at what's given to us. Well, from the energy diagram, we have a single step, 2-step, single step. All right, I'm almost done clicking that button. Sorry about that. So we go first step, 2nd step, another single step, and then a 2-step. Okay, if it's 1 step, then we know it's SN2. If it's 2 steps, we know it's SN1. 1 step, SN2, 2 steps, SN1. Now we look at the rate laws that would be generated if that was the case. So SN2 is going to have a bimolecular, both the C and the nucleophile are in the rate law. In SN1 it's just C. SN2 it's C and the nucleophile. And in step SN1 it's just C. So we can go up and take a look at the rate laws given. So D is wrong and C is wrong. Those do not match the energy diagrams given in terms of number of steps and rate laws. So we're left with these two, and now we need to analyze the data, right? So we look at trials 2 and 3. We double the amount of hydroxide in 2 and 3, holding C constant, and we look at the rate. The rate doubles, so therefore we have SN2, the nucleophile is in the rate law, and we would pick A. Okay, here we're given a problem that says, what can be done to increase the rate of this reaction by a factor of 4? Now, one thing we could do is increase the temperature, but we're looking at changing the concentration of the nucleophile and the electrophile. All right, so first we need to take a look at the structure of our electrophile. And we see that it's a zero order, meaning it only has one carbon atom altogether. So that carbon atom isn't attached to any other carbon atoms. So what we do know then, if it's primary or zero, it's SN2. So we can write the rate law that has both the electrophile and the nucleophile in it. Okay, so if we want to multiply the rate by 4, there's a couple ways we could do it. We could multiply each one of, we could double each of the concentrations here. We could times 4 the electrophile, keeping the nucleophile constant. Or we could times 4 or quadruple the nucleophile, leaving the electrophile constant. All of these will contribute to a total rate order of 4. Okay, here's another secondary carbon. So let's take a look at its analysis. All right, so here's the nucleophile in the rate law. That's the number 1 step. We look at trials 2 and 3. We see that when we change the concentration, when we double the concentration of hydroxide, the rate does not change. So we double hydroxide, rate stays the same. So we know we're dealing with zero order nucleophile, which is SN1. So let's look at that mechanism in detail. So step 1 is the breaking of the carbon-iodine bond, leaving behind a carbocation. That step is slow. Then an opportunistic nucleophile, hydroxide ion, waits for that bond to break, then reacts at the carbocation, giving us this product. And that happens fast. So it's a 2-step mechanism. First step, slow. The rate order is just the electrophile, and we would have SN1. Okay, so this is the thermochemistry analysis of delta H and delta S. So what we're looking at is breaking a carbon-sulfur bond and replacing it with the carbon-chlorine bond. All right, so carbon-sulfur more or less is almost electronegative neutral. And then we have carbon-chlorine, which is a polar bond, 0.5 difference. And so we'd expect the carbon-chlorine to be more polar, stronger, and a lower potential energy. That gives us going from high to low exothermic reactions. Okay, so if we want to do the delta S analysis, we see gas plus aqueous is aqueous plus aqueous. So we're losing gas, high entropy reactants, low entropy products, and that gives us delta H and delta S are both negative. We could plot delta G versus T, and also construct an energy versus entropy diagram that shows us that this is product favored at low temperatures, reactant favored at high temperatures. All right, so what is true with compound D reacting with bromide? All right, so let's take a look at compound D. What kind of carbon is it? Oh, it's a primary carbon. Whoops. So primary carbons are going to react exclusively in Chem 152 as SN2. So primary carbons SN2, let's do a summary, are bimolecular, single step, nucleophile in rate law, right? That's really important. Tertiary carbon for SN1, so tertiary carbon is SN1, it's unimolecular, has a carbocation, and the nucleophile is not in the rate law. Okay, so that means that if it has an intermediate, so that means B is SN1. C does not change rate with concentration of the nucleophile, that is SN1 also. But it takes place in a single step, is it definitely in SN2? Alright, so let's make a summary. 0 in primary carbons, exclusively SN2. Secondary, it depends on data, like we saw in this video. We analyzed 2 data sets. Really depends, does the nucleophile change the rate of reaction? If the answer is yes, it's SN2, and if the answer is no, it's SN1. Alright, so we look at the graph of rate versus concentration of the electrophile. In both mechanisms, that's linear, because the electrophile is always in the rate law. If we look at the rate versus nucleophile for the two, we have first order using SN2 because it is in the rate law, and zero order in SN1 because it's not in the rate law. Alright, so with that, I hope that the homework is more straightforward. But if you have any questions, please let me know.